Good day, and welcome to the Plant Engineering webcast, Understand and Control Compressed Air System Costs, sponsored by UE Systems Incorporated. Today we'll be joined by John Ghislaine of Ghislaine Operational Efficiency. He is also a Compressed Air Challenge instructor. I'm your moderator, Kevin Parker, and I'm happy to join you today on behalf of Plant Engineering. Today's presentation can provide continuing education credits. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RECEP at recep.net. A certificate of completion will be available for each participant to download upon successful completion of a test at the end of the presentation. As such, it does not include content that may be deemed or construed to be an approval or endorsement by RECEP. To take the Learning Unit exam, use the Learning Unit exam tab option at the top of your screen. The exam will open in a separate browser window. You can complete the exam after the webcast. However, the link will break when the webcast signs off. The exam will be posted on CFE Media websites with the on-demand version of this webcast. The exam is for one RECEP ASEC Certified Professional Development Hour. Here are some tips to help you get the most from today's webcast. If you're experiencing issues with your slides or audio, refresh your browser or click the Refresh Media button directly under the presenter's picture. You can control the volume by adjusting your computer or by adjusting the webcast platform. If you are having technical problems with audio or the slide presentation, click on the question mark at the top right-hand corner of your screen to access a list of system checks to try before contacting an online technician. If you do need a technician, type a message in the Ask a Question box, and someone will get to you as quickly as possible. Type questions for our speaker in the Ask a Question box on the left-hand side of the screen. The live Q&A session will begin after the presentation concludes. Today's webcast is being recorded. You will receive an email within a week with the link to the on-demand event. To download a certificate of completion, a PDF copy of the presentation, and other additional resources, use the Event Resources tab on the left-hand side of the screen. These documents will also be available with the on-demand version of this webcast. Before beginning the presentation, we invite you to view the short video provided by our sponsor, UE Systems, Inc.
UE Systems has been delivering the highest quality ultrasonic detection instruments for more than 40 years. And now, they are bringing their world-class education right to your desk. Introducing UE Systems Compressed Air Survey online training course. You will be walked through the fundamentals of leak detection, preparation and planning for a compressed air survey, the different types of leaks, the ultrasonic instruments used in a leak survey, and an in-depth look at how to use that equipment. This e-learning course will teach you how to analyze and report your findings, how to log your results into the DMS software, and the corrective actions you should take upon completion of your compressed air survey. The course is broken up into 6 segments with a quiz at the end of each one. After completing the online course, a UE Systems certified learning coach will remotely walk the student through the practical exam performed at their own plant. For more information, contact UE Systems, the leader in ultrasound detection.
Welcome back. I'm now happy to introduce today's presenter, Joe Ghislaine, Principal, Ghislaine Operational Efficiency, and a Compressed Air Challenge instructor. Joe has experience in both commercial and industrial facilities and expertise in energy efficiency, energy management, and lean manufacturing in the automotive industry and the supply chain. A Six Sigma black belt with extensive lean training, Joe is a certified energy manager and a certified practitioner in energy management systems. Joe, welcome to today's webinar, and please go ahead.
Thank you, Kevin. So, as Kevin mentioned, my name is Joe Gissling, and thank you for joining this presentation and this webinar. This is just a little bit about me. Those are some of the credentials I had. As he mentioned, I'm a compressed air challenge instructor, and from the compressed air side, a certified compressed air system specialist. I've been on the board of directors and an instructor. I have my own consulting company, but as Kevin mentioned, my background is really in the automotive. I spent 31 years with Ford Motor Company before I retired a little over 2 years ago. So what I want to talk about first is the Compressed Air Challenge, because many of you haven't heard about it, but it's a nonprofit voluntary collaboration, and that includes end users, it includes the manufacturers, the representatives, distributors, facility operating, consulting, research agencies, energy efficiency organizations, the Department of Energy, and utilities. And really the key to this organization is they have one purpose in mind, and that really is to help you improve your performance of your compressed air system. Compressed Air Challenge actually was brought together, all those stakeholders 20 years ago, and we've been going through and teaching and training compressed air system efficiency ever since. This is just some stats, a little bit of stats on trading. It really does solve problems and save energy. So CAC has done more than 15,000 compressed air end users since it started in 1999. We have the 2 levels of fundamentals and advanced. We also partnered with Department of Energy to create Airmaster Specialist training. We also have an end user operator awareness, and of course the best practices magazine. Best practices manual that we have, which was updated in 2009, but it really is a source book for compressed air. So wanted to let you know of that resource. And why does the Compressed Air Challenge care, and why should you too? Well, in the United States, compressed air systems account for over $5 billion a year in energy costs, according to the Department of Energy. It makes up 10% of the electricity used in the United States, and it also represents 16% of all motor systems. So again, it uses a lot of energy and our resources that we have, as well as cost. And popular contrary belief, it's not free. Most of the people in production and that use it, they don't know what the cost is. They don't know how much it costs. But it definitely is not free. And as you'll see in this presentation, it is a very costly utility. It's oftentimes called the 4th utility, and for good reason, because it does go through and cost a lot. So as an example, at 100 PSI, that can range anywhere from 18 to 32 cents. That should say per 1,000 cubic feet. I apologize. This must not have been the updated one, but we'll get that changed before it goes online. But that's per 1,000 cubic feet of compressed air. And again, it depends on whether it's air-cooled, water-cooled. But the whole thing is you have to take the total cost in it, because there's also ancillary equipment that goes along with the compressed air system. So this cost just isn't about what the air compressor uses. Remember, you have dryers, you have aftercoolers, you may have stuff with intercooler cooling. So it really depends on what it is and how much it works. In the auto industry, where I came from, it came anywhere from 10% on the component plants to up to 40% in the stamping plants. And air leaks is a huge piece of it. It can be anywhere from 20 to 30%, and that can be as high as 50% in a lot of facilities. And in the Ford facilities I dealt with when I was the global energy manager, that ran from anywhere from several hundred thousands of dollars to even millions of dollars a year just in compressed air costs. And it's not very efficient. This graph illustrates that for every 7 to 8 horsepower you put in on the left-hand side of this graph, that bottom blue part you see on the right side of the graph is the useful work. You only get 1 horsepower out for every 7 to 8 horsepower you put in. You've got the losses that go between the electrical motor and the switch gears, which isn't huge, but there's a loss there to the shaft power, and then the losses you have in the system. And the largest piece of this happens to be heat of compression. So what compressed air air compressors, if you think about it, they are terrible at making compressed air, but they are really great heaters. Probably 80% of it goes into there, and we'll have a slide on that a little bit later. So how do you go through and reduce cost of compressed air? Really, you want to look at the system efficiency and maintaining that efficiency. And you really want to go through and take a best practices approach using a systems approach. It's not just about the compressors. As a powerhouse chief, I always said, if they don't use it, I don't have to make it. And that's true. This is a supply and demand, and it really is about the entire system and how effective you're managing the system and those demands. So this presentation is going to concentrate a lot on the demands and not as much on the compressors, because again, most of the concentration is in the compressor room, and you have experts that can help you with that. It's really about understanding where you're using it and where the losses are, which is getting out in that demand in the production areas, in the facilities where it's actually being used. So today we're going to go through and we're trying to talk about the awareness approach and training. We're going to look at calculating baselines, what you need to do that, aligning supply and demand. We're going to talk about controls and, again, the demand side strategy, a bit about maintenance and design. The real key is you want to go through and publish those savings, putting it into dollars, because that's a universal language. You talk to plant managers and controllers and, presidents of an organization, you start talking about CFM and PSI and KW, you might as well be talking a foreign language to them. But you start talking dollars, they understand that and are very aware of that. And then, of course, an important part is the employee awareness and making a continual improvement in your system, and then integrating it into current process you have. And we'll again talk about that later in the presentation. Really, the key was we talked about baselining. If you can't measure it, you can't manage it. That's said many times. So you really want to go through and look at establishing a baseline using your flow and your KW. You want to understand a system profile so you know the dynamics of it. And you want to convert that compressed air usage again to dollars. And you want to go through and take that and put it a cost per widget. So whatever your organization is measured on, putting it in that same measurement is very, very powerful. It now puts it on the same level as putting it in for material cost, labor costs, anything that goes into that cost for whatever the actual organization is making or whatever they actually measure themselves upon. So baselining, again, really we want to go through and look at the operating of the compressed air system, how efficient it is, and really varying in the production requirements and putting it in terms of production. The measurements you really want to look at, you want to go through and look at power. So we're now going to be talking about KW, and we're going to talk about energy, which is KWH. We're going to talk about pressure in PSI. We're going to look at leak load. So how much are you actually leaking? And then, of course, flow, which is CFM. And when you do this, you want to make sure that you take the measurements before and after any changes, especially with fixing leaks. Again, when we take these, we want to see how much we've actually saved and put that again back into dollars and showing people how much it has. Once we fix the leaks, how much have we actually saved, for example. Tips on baselining. We really want to go through and look at the data. You really want to go through and be able to do it under normal condition, other significant conditions. So that's going to be different production levels, whether it's a weekend, whether it's difference between first shift versus second versus third, any seasonal variation. And then anytime you make a change in your production, change in your operation, add equipment, delete equipment, you really want to know what's happening in that baselining and make sure that you keep up with that. And the real key of knowing what that is and why you want to do that is be able to align the supply with the demand, because each one of those different operating patterns or operating modes is going to have a different usage. And so we need to go through and align that supply with whatever that demand is happening. So we really want to go through and understand that the system demands drive the supply requirements. The number of compressors, the duration, all of that, and the system dynamics really tells you what's happening in the system. And again, we have to be able to have the right number of compressors to be able to control that. And the relationship does require the monitoring of not only the compressed air, but understanding what's happening in the end uses and how the end uses are actually affecting the system itself. So one of those ways we do that is going to be through compressor controls. Now, compressor controls, really the reason we want to do this is to optimize the right mix. Again, number of running ones, shut off unnecessary compressors, delay bringing them on, and of course, another big piece of that is safety. So the controls the controls of a compressor go through and play an important role in doing all of these pieces, making sure that you have the right compressors running, the ones that are base loaded or that are better at base load or base loaded, and the ones that are used for trim that have better part load efficiency are running. And you want to go through and minimize those numbers. And that's really what we want to look at when we look at compressor controls a little more in depth. We want to understand the system dynamics, the capacity of what it is. You want to go through and run as many of them at full load, base load as you can, and use only one for trimming the variable load. For multiple compressors, you can network them together and then shut off and trim as necessary. And then as you get bigger systems with more requiring more sophistication, you can start using some of the sequencing controls and what we refer to as global controls like energy management systems that can go through and do not only a mix of different types of compressors, but can also look at other ancillary equipment and how effective your overall system is actually running. So system control, again, you have to operate the right type of compressors under the right conditions. So this just gives you an example of what you really want to go through and look at and where you're at. And it also depends on the system controls, because rotary screw machines, for example, when you go through and put them in modulation, if you start running them below 40 to 50%, then they become very inefficient as a compressor. As a matter of fact, when you go through and down to zero, actually a zero condition for a modulating machine will still use 70% of the energy. Variable speed machines really should only be used as trim. When you use them as a base load, they are inefficient because, again, they're designed to run at a lower load. The biggest thing right now in the compressor industry is variable speed drives will go through and take care of all of your problems. They just want to let people know it's like any other thing. It's a tool in the toolbox, so it's got to be applied correctly. You don't want to have all variable speed machines in your suite of compressors because, again, they only work well at a part load efficiency. Centrifugal compressors are great for efficient base loads, but they do have limited modulation control. And then, of course, the old double-acting recips, if you have those, they are very efficient at part load operations and run very well and very efficient, both at part and full loads. So another part of our control scheme you want to be aware of, and again, it gets back to system dynamics, is being able to use storage to control the demand. Air storage is really receivers. It's big tanks that are used to meet any demand events. The ones that are close to the compressor are called primary storage, and they react to any system demand. Then you look at secondary storage. Secondary storage we use to locate near the end use to go through and handle those high volume intermittent uses that happen in a system to go through and minimize their impact on the system. And then another optional device is a pressure flow controller, which is used with storage that can go through and hold a tighter band, monitoring the downstream pressure and using that stored energy to quickly react to the demands that they have. What is the most efficient compressor? So I'll let you just think about that for a couple seconds. Maybe you can go through and in your mind have what the most efficient compressor is. And it goes back to controls and controls, but the most efficient one, remember, is the one that's shut off. Now, you've got to remember, one of the big parts of controls is going through and being able to minimize the number you have on and making sure you shut them off. Because, again, it is important that you have the minimum amount of compressors running to meet the demand you have, and I should say effectively meet the demand you have. And the next portion, again, is looking at demands themselves. So when we're looking at demands, we want to go through and look at the components. So this just gives you a typical component. that we talk about in compressed air training, CAC training. Again, its normal production we have is about 50%. It's showing about a third in leaks. And then we have what we refer to as inappropriate uses. And then this increased demand due to excessive system pressure, which most people call artificial demand. So if you want to cut costs and reduce unproductive demands, we really need to look at those ones on that top half of the chart you saw. The non-production, what's really wasting, the leaks, the inappropriate uses, and then, of course, the artificial demand. So we also want to look at this is the excessive and high system pressure that goes along with this, because that is one of the things that causes artificial demand, as you'll see. So first, let's talk a little bit about inappropriate, what we call inappropriate or potentially inappropriate uses. So why do we want to look at using direct electrical conversion? So why do we want to use, rather than use compressed air, why in the world would we want to not just use a motor directly? So here's a quick comparison. So first of all, we talked about the efficiency of a compressed air system, and it really is as low as 10 to 15%. So again, it's not very efficient. But what about the difference in cost between using air versus an electric motor? So this gives an example, again, 1 horsepower air motor versus 1 horsepower electric, 5 days a week, 2-shift operation, 10 cents a kilowatt hour. So for compressed air, it's going to cost you $2,330 a year to run. For electric, it's going to cost you $390. So again, you can see the real big difference in cost that you have when you look at the difference between using compressed air versus directly using electric. So what are some of the inappropriate uses? Really, this is the list that we have from Compressed Air Challenge. I'm not going to go into details on each one of these, but really, anytime you're using air to blow, to mix, to go through and atomize, to go through and transport materials, to create a vacuum. My favorite is that one of there, it's the personal coolers where anybody with a scratch-all and a rubber hose can make themselves a nice little air cooler on them, which still with an oil system, you wonder about the real quality, but at least people feel that they're getting a little bit more air blowing on them and feel a little bit better. Handheld guns or lances, again, diaphragm pumps, cabinet coolers, and of course, any air motor, pneumatic cylinders. Those are areas, not saying that you should get rid of them, but they are definitely areas you want to go through and explore. Because again, back to that previous slide, if I'm going through and doing some mixing, for example, with an air motor, why can't I use electric? So some of the examples of these that I have done in my career when I was at Ford is going through and changing pneumatic mixers over to electric motors. So in the paint shops, being able to do that. Now, you may have to use explosion-proof motors, but it is something that can be done. Pneumatic tools, we switched from DC, which saved energy and also increased quality. Any air blowing that we had using high-efficiency nozzles or low-pressure electric blowers, going through and eliminating the personal coolers and cabinet coolers using either fans or AC units for the cabinets. Again, vacuum generation and vacuum genturies, either going through and replacing those with high-efficiency vortex cups or smart pump vacuum systems. So again, finding ways to go through and create and take advantage of that inefficiency that we have with compressed air versus electric. And of course, leaks. Department of Energy says even if you have a tight system, you'll still have leaks in a 10% leak rate. I like saying it's like my house. I fix one thing here and another thing over there breaks. Same with a compressed air system. As you fix them, you're going to have other leaks appear, and the real key is to have an ongoing program to take care of it. Again, not uncommon to find 20 to 30% leak rates, and it's very costly. This gives you an actual example of the cost of compressed air. If you look at that quarter-inch leak, again, this is calculated 10 cents a kilowatt hour, assuming a constant operation, 100 psi. It's almost $17,000 a year for that quarter-inch hose that you have. And again, when you talk about air leaks, I want to go back to the inappropriate uses. Remember, some of these air leaks that we call inappropriate uses are quarter-inch tubes that may be blowing dust off of parts or drying parts. But that's the cost that you have there. So again, back to the cost, whether it's a air leak that happens that's not planned or one that you've designed into the system, it is very costly. Now, the good thing about compressed air leaks is just like a compressed air system, it isn't very efficient neither. So on the bottom, we talk about this perfect this assumes a perfect orifice. When you see air leak charts, most of them assume a perfect orifice. Well, what's that mean? Well, not everything is a perfect orifice. So if you have a nice, clean piece of copper tubing, it's going to be about 98% efficient. And if you have a crack on a pipe, it might be down to 60 to 70% efficient. So again, it depends on what type of leak there is, but either way, it is a costly thing. The only reason we bring out that piece is if you're estimating it so you don't overestimate what your leaks really are. And of course, that piece we talked about, artificial demand. First of all, what is artificial demand? Well, artificial demand is increased demand due to excessive system pressure. What does that actually mean? Well, what it means is I'm having to have my pressure much higher in my system, which causes me to run more compressors longer to keep it up. And what causes it? Again, you've got two things, unregulated air leaks, and then anything that's an assumed high pressure requirement. So something that may be an individual thing that uses, and when we say high pressure requirement in the compressed air challenge, we talk about anything that is higher than the average pressure you use in your system. So do you have these loads that that affect your system? And we'll talk a little bit more about that coming up. But the one I want to mention is the unregulated air leak. So there's a definite relationship with pressure and flow, and that's basically through an air leak, and that says the higher the pressure, the greater the leak. And what happens when something leaks? What does it do to your pressure? It lowers your system pressure. So if you have to maintain the system, what do you have to do? Add more compressors to do it. So that's why we're calling it an artificial demand. The air leaks, because of running at a higher pressure, are causing me to have to run more compressors to maintain that system pressure that those leaks are dropping in the system itself. So again, that's where we get this term artificial demand. But make no mistake, it's a real cost. And system pressure reduction, well, what does that look like? So there's a rule of thumb that says for every 2 psi, it's 1% efficiency decrease. And at 10 cents a kilowatt hour, 100 horsepower, running 80 psi rather than 100 psi would save you $6,500 a year. So again, a big cost in just lowering the pressure. Well, you just can't go out to your plant and start cranking pressure down, because the other thing I can tell you as somebody that's had to run these systems is I'm going to be preaching about energy efficiency, but I will tell you, nobody got fired for using too much energy. Taking down an entire assembly plant in production, that gets a little bit dicey. So you do have to be out there. So I'm not advocating, and neither do we in our training, advocate run out there and just start turning down the pressure to save money. You have to go through and look at the system and look at where you can do that. And the way you do that is to look at the end uses. So you got to look at the air quality requirements you have, any high pressure applications, and those high volume intermittent demands that you have. You really want to go through and look at these and say, where can I go through and make changes in the system that's causing this pressure to drop, that I can go through and now basically be able to lower the entire pressure because I've gotten rid of these issues that happen in the demand side. So real quickly for the air quality, obviously anytime you add a filter, it's a pressure drop in the system. Anytime you add any kind of a fitting whatsoever, there's a drop with it. So you really want to look at the end use and treat it to only what you need that's required. Because if you go through and over-treat the system, it's going to be more capital investment, higher operational cost, additional maintenance, and not to mention the pressure drop that comes in, because the more filters you put in, the more drop you have, and the better the quality, the higher the pressure drop is in the filters. So you want to go through and use low pressure drop long-lasting filters, and then you want to replace those elements when that cost exceeds the amount of replacement. The next one is a high pressure application. Again, a small percentage of the load can require high pressure, so you want to go through and understand that. I throw this little example in there. I was doing an actual an energy audit at one of our buildings that was a North American automotive operation, which was about a 14-story office building. And so I was going around expecting to find the normal stuff you find in office buildings. And then I went downstairs into the executive garage and found that they had an air compressor running at anywhere between 95 to 110 psi, driving the entire system, which for things like controls, you need maybe 30 at max, even with that big of a building. And I found out it was because they had to go through and fill the tires up on any time that the executives would come in with their lease cars, they'd have to fill the tires up. And so basically I told them to go get a smaller compressor and take the entire thing down. My point to this is you'll find high pressure requirements driving systems, and you really need to go through and look at those. So you don't let it drive your entire operating pressure. You need to go through and test those assumptions. If the assumption it really needs to do it, you need to find better ways to do it. That could be modifying the equipment, isolating it under these ways that we have listed here. The whole thing is you want to go through and make sure that a small percentage doesn't require you to maintain that pressure up there. You want to take advantage of being able to lower it for that 2 psi and 1% efficiency. And the high volume intermittent uses, again, these are going to be things, they could be dust collectors, they could be transport, they could be anything that uses a large volume quickly. Again, that when it happens, it can disrupt production, disrupt operations by dropping pressures. So what you want to do is you want to use storage to minimize these effects. You want to properly go through size, calculate it, which we go through in our advanced training. But this you go through and because it's a short duration, the idea is you go through and take the time that it is not actually running to fill up the storage tank. And then when the demand hits, you've got localized air that's there that can go through and serve that demand. And then, of course, inadequate piping can also lead to pressure drops and other problems in the system itself. So you really need to be aware of that as well. So a case study that I had was the Woodhaven stamping plant that we worked with. Again, they had a leak detection. They repaired seals in the presses. They went through and looked at the pressure drops and reduced it at various points. Removed orifice plates in there and put in insertion meters. Also worked on high pressure assumptions. There was a thought that that a lot of the robots and some of the lift devices needed a higher pressure than required, and so they looked at the header production, actually reducing the header pressure, and they were also able to go through and remove satellite compressors and dryers that were on there. So the results that they had, they reduced it by 18%. They shut down a centrifugal compressor, 800 horsepower. They also were able to shut down those satellite compressors. So there was 6 small 30 horsepowers that were able to be shut down. They reduced the system pressure by 5 psi, and the savings was 7.9 million kilowatt hours, which was a savings of over $400,000 a year. So again, taking these actions was a huge savings for this plant and facility. And maintenance, I'm a big maintenance proponent with my background. That's where I came from. So again, understanding that the proper maintenance of both the supply and demand, that's critical to happen. It always frustrated me that it was considered a necessary evil. And it's one of the first places that the budget gets cut. Either that, or in the auto industry, it's very cyclical. When we would be selling and have the money to do the maintenance, we could never shut down because we were running production all the time. When it came back down and we were able to lower production, so we were able to actually come in and work on the equipment, now we didn't have the money because the cost was down. So it's one of the places that gets cut first. And so really what we want to do is we want to come back to this thing of dollars and show them that it's penny wise and dollar foolish not to do the maintenance that you really need to do. And of course, the compressed air system should just be like production equipment. It should follow a total predictive maintenance journey. You start out with reactive, you look at doing preventative on a schedule, then you start using things to make it predictive and then make it really proactive. So you're fixing things before they break. So again, it should be no different than your production equipment. And why? Because the maintenance losses are huge as far as cost. We already talked about pressure drops across filters. That 2% equals 1% efficiency goes into real cost when you start talking about main filters. And then again, increased temperature and moisture. It increases the loading, reduces quality, shortens the life of the equipment, and just costs more money in general. And then, of course, things like inlet filters. Dirty inlet filters, they're going to reduce capacity. And the rule of thumb here is for every 4 inches of water drop across an inlet air filter, you lose 1% efficiency. So again, take these efficiency things and convert that necessary evil to, I need to change this because it's costing us more in operational costs than if I just went and changed the filters, okay? And of course, production downtime is a huge one. I'm not going to go into a lot of details with this one, but when I was the powerhouse chief at Chicago Stamping, we had recips that hadn't been maintained and had a large downtime. The long story short of this was I put together a preventive maintenance system and put it in place, and I cut the downtime of those by 90+% and saved a lot of money because it used to take the production levels down. But if you don't go through and show and convince people that you need to do it, you'll never get to that point, and you've got to be able to show what the costs are. And of course, we talked about this a little earlier, but I want to emphasize this. Biggest cost in maintenance is air leaks. Air leaks are huge. We talked about that. Again, it causes pressure drops in the system. We talked about this. Elevated pressures, increased compressor operation, higher energy costs, increased maintenance, unnecessary additional equipment being bought. And then, of course, the leak itself, which you saw earlier, for a quarter-inch leak, it's over $16,000 a year. So air leaks are always a big problem and will continue to be a big problem. So again, did you know a $200 leak can be felt and not heard? An $800 leak can be felt but not heard. And if you're hearing that air leak, it's at least $1,400 because that can be felt and heard. And again, this is at 10 cents a kilowatt hour, 8,760 hours. So this slide kind of goes to, what do you do if you can't hear it? Well, how do you find them? Ultrasonic leak detection. Ironically, this is sponsored by UE, who makes ultrasonic leak detectors. And they had a video in the beginning of this, which shows exactly what it is. But again, this is a slide from the Compressed Air Challenge, again, going through and showing how does it work. They mentioned that in the video, but just as a reminder, it really is ultrasonic high-frequency waves, and the short wave signal goes through and drops off quickly. So the closer you are to leak, the higher the signal is. So it makes finding leaks very effective to go through and do, either from a pressured system, which you see on the left, or a vacuum system, which you see on the right. So anytime you're changing from a high pressure to a low pressure, you're going to get ultrasonic waves that come off of this. And the detector is a great way to go through and find those. And then, of course, how do you do it? You need to really implement an aggressive air leak program that finds and fixes the leaks. Leak tag programs, you should establish it on an ongoing basis. Again, we talked about ultrasonic leak detectors. You want to go through and put the cost and estimate those air leaks. The most important thing is fix them. It sounds funny, but I had plants that did a great job of putting them in their preventive maintenance system, going through and estimating the leaks, putting the tags out there. They just weren't able to get the overtime to fix them. So you got to go through and put those costs in front of people and show what it's costing and go through and fix them. And I am a big believer in, if you can do a find and fix program, which basically says fix as many of them as you go when you're doing your leak tag, do it. Publish the savings to results. And again, you need to go through and include this in an awareness cost as part of your energy awareness, and we'll talk about that coming up with a case study example I have coming up. I don't want to go through, and I would be remiss in going through and not at least touching on system design. So 80 to 90% of the operational costs are, pretty much designed when the system's in there. So you've designed the equipment, you've bought the equipment. Really, all you do when you put it in is now optimizing. So if I put something in that's inefficient to begin with, I can't make it more efficient unless I remove it and put something else in its place. So we want to talk about total cost. This is, again, a chart from the compressed air challenge on a 75 horsepower motor. Compressed air system. The equipment costs $30,000. The maintenance is $3,000 a year. So you can see there that the maintenance at $3,000 for the 10-year life expectancies, $30,000, and it costs you $26,000 a year, 10 cents a kilowatt hour. So as you can see, within the first 2 years, the cost of the electricity has already dwarfed the cost of the equipment. And I'm not sure about everybody that's listening in, but I do know that I've had through my career work with the purchasing folks, because their main thing is to get the lowest cost they can possibly get to put in. And so you need to be able to explain, this is why I need something that may cost a little bit more, but uses less electricity, that's more efficient to go through, why you need some of the controls, and why you need some of the things that may cost more to get thrifted out. Because again, in the long term, you're talking about saving costs and saving dollars. And it's important that for whatever company you're working for, that you're able to go through and reduce those costs and show them that, again, they can go through and save by spending a little more at first and being able to do it. And then, of course, the total cost piece of it, I'm not going to go through all of these, but I'm putting them up so you can understand, portions that you want to look at. Again, you want to implement the low-cost actions. You want to go through and look at the benefits over the entire lifetime of it. You want to go through if there's utility rebates and use those. Again, you're going to talk about the right mix of compressors, pressure drops in a system, going through and paying less for something that has paying more for something that has less of a pressure drop really can be cost effective, because sometimes even upsizing pipes, for example, may not be a huge cost in the initial portion of it, and it can save huge in the long run. So again, and then the one that we mentioned was heat recovery, because again, compressed air systems are very inefficient, and they do really great job of going through and producing heat. So this graphic just shows that big red arrow in the middle there. All of the green ones are the losses that get there. You've got one little one that gets to the point of use, and that big loss, that arrow that goes out there, is the heat loss. So if you can take advantage of heat and recover that heat, you can at least go through and make the system a little more efficient and take advantage of stuff that's just going, that you have to actually pay to get rid of. You have to run an intercooler and an aftercooler, and you have to, whether it's water cooled or air cooled, you have to be able to go through and get rid of rejecting that heat when it goes into the system. So some of the areas you can look at going through and doing it. So for air cooled rotary screws, looking at ducts, recovering space when outdoor temperatures are good. So again, I'll preface that this works like where I'm at in Michigan, but if I go with one of my other instructors who's down in Phoenix, it doesn't work very well. But again, if you have something that you can offset HVAC requirements for heating, perfect example. Water-cooled compressors, you can go through and use heat exchangers to go through and recover it and either put it in for heating or go through and use it for sources that may be used in the production process. And then you have engine-driven compressors that can do the portion of the air compressor, but then you also have the heat off the engine you can go through and do, and the exhaust stream. And for larger systems, gas turbine systems can also do the same thing, and you can also make steam off the exhaust that comes off of that through a waste heat recovery boiler. So it allows you to go through and use different things that you can go through and do for heat recovery sources. And some of the examples that we have, I mentioned the supplemental heating for cold water areas. So again, looking at industrial process heating, water heating, makeup air, boiler water makeup preheating, and drying compressed air through heated compression dryers for oil-free machines. And the final design tip that I want to leave you is all compressed air systems were originally engineered and then they grow. The real truth is when you're in a manufacturing facility, over time things change, processes change. You have to go through and look at your system and keep evaluating that system and its efficiency. So that's why we talk about understanding the supply and the demand, because again, it constantly changes and the dynamics is constantly changing over time. And so you want to be able to go through and understand that to keep the system maintaining that system integration and efficiency. And another big part then is awareness. So my big thing was people are the ones that use the energy. They're the ones that need to be involved with it. So you really want to get the people that use it involved. I'm a firm believer that nobody goes to work that works in any capacity at a company and says, gee, I want to do a terrible job today and I want to waste a lot of money for the company. People want to do good things and they just don't know what the costs are. So awareness is a big part of what you want to go through and do. So my example here is if I told you that you could reduce compressed air usage and energy by buying jackets, hats, keychains, pizzas, would you buy it? Would you say that that's something you can really do to go through and save energy? Well, that's exactly what the Monroe Ford stamping plant did. The actions they took, it was an hourly led energy team. The plant manager got them red jackets and they would go through and they would wear them so they stood out, and they went through and implemented an aggressive awareness and air leak program. They went through and they gave away buttons, keychains, hats, t-shirts for finding and fixing leaks, and pizza lunches were for passing the red coat energy audit that they would do every weekend on shutdowns to make sure people were shutting off equipment. They would also do things like hang tags on saying this is what this machine costs and putting it in terms that people really understood. So they posted leak boards throughout the plant to track process, and they used the Ford Communication Network, which were monitors that we had in all of the break rooms, to go through and send messages out on costs throughout the plant. The results, they went from using 17.4 million cubic feet per day to 9 million cubic feet per day. The non-production usage went down, so we're talking mainly air leaks, from 5,400 CFM to less than 600 CFM. They were saving over $2,000 a day in electricity costs. And the big important thing is it really created a culture of change in the plant, not only an awareness of energy, but the usage and waste and what the costs were. So again, it's really important to keep people involved and have them understand what these costs are. So the key components you want to have in an awareness program, really, you want to go through and target the operators and end use for the training. That's going to also include maintenance folks as well. So you want to use site-specific examples. It's always better if they can see something that they see every day. You want to give them an overview of the compressed air system. You want to understand an understanding of what the actual demands are, what leaks are, inappropriate uses. You want them to understand that it's inefficient and very expensive. And the real thing that you want to get across is they are the key to using it wisely to save energy and money. As the global energy manager at Ford, I'd have a lights, I'd have a monitor, I'd have a computer that I could shut off. So that really does nothing for energy. The whole thing is getting the people that really use the energy out there, going through and understanding what it is and trying to reduce what that is. And so this is a key part in any continuous improvement plan. So compressed air challenge, we've actually put together one that I'm just showing as an example. It's an operator awareness. It has all of the elements that I talked about. The training's customized to each site and facility. It's delivered like a lunchbox talk of 30 to 45 minutes. So it's perfect for team meetings, toolbox talks, safety things. And really the key is it's also has flexible delivery, because you can go through, we've made it so the plant people can do it themselves and it's just ordered online. They can have a compressed air challenge instructor help, or they can have it delivered. The real key is that you want to go through and make sure that you have something that is making people aware. And this is just the front page of it. But the real key message that comes across in this is that cost of compressed air is very expensive. End uses of compressed air, you got to look at whether it's appropriate, inappropriate, or it's an air leak, and that the person that's taking the training, the end user, is really the key to making sure that it's used wisely and you save money. And the other pieces of it include, the normal rules of engagement, that you want to make sure that nobody feels threatened when they bring something up. Definitions, cost of compressed air, the supply system, the demand system, the air leaks, and then they're the key, again, reiterating that that's it, and that you have a contact for somebody to contact in the plant and facility. So again, it gives the ability for an organization to go through and broadcast what these costs are. And then what I'll call Joe's final thought: for lasting energy efficiency, it's got to be part of what you do, not additional to what you do. Somebody asked me what it was like to be the global energy manager at Ford, and I said it was like selling ice cubes to Eskimos. You have to convince people that already have a lot on their plate to do more. So you want to build it into things that are already happening if you want to go through and make it worthwhile. So some of the processes that we integrated it into when I was in that role, we went through, I have ISO 50000, that wasn't around back then, but we did put it in our 14000. It was part of the sustainability, first the environmental report, then the sustainability report. It became part of the lean manufacturing system, which a lot of manufacturers are going either lean manufacturing or world-class manufacturing systems. The real key is to get it in there. So the Ford production system had energy as part of it, and it even had its own energy operating system, which was the EMO system. And another key thing that I did was to try to get it actually into plant manager scorecards. So they were actually being tracked as part of their performance was included an energy component of that. So making sure that it goes into what you do. And of course, always publish the results on how much is saved, and continue to work on continual improvement for the actual system itself. So you want to go through and make sure that it is continually improving, and it's not just a one system thing. So with that, to maximize this, again, we want you to take a systems approach. I've just got some information again on the compressed air challenge that you guys can go through and look up. Again, it gives our trainings, which goes more in depth to the actual topics we reviewed today, and the actual ability to go through and do these pieces of it. So going through and has best practices manual. It also has case studies, fact sheets, articles, all of that stuff. And we also have a source book that we did with DOE. And for those of you that want to go on for certifications, the Compressed Air Gas Institute, which is one of the actual sponsors, as you saw for the Compressed Air Challenge, now has certifications. They have their certified compressed air system specialist, which is up and running now, and they're working on the compressed air system assessor. And this is really to start kind of expanding on what we've worked with them in the past, because they also have data sheets that they have that you can go through on KGI's website. And for any of their members, they actually have certified outside parties that go through and tell you what the efficiency of each of the compressors are. So again, KGI is a good organization. Obviously, they're the main ones for understanding compressed air. So I wanted to make sure you were aware of that as well. And this is my contact info that will be available. You guys can look at and do. And then with that, I think that just takes us to questions and answers, I believe. Or do you have something then, Kevin? I think you're taking it over from here, right?
Yeah, Joe, thanks. A great presentation and of great interest to our audience of nearly 300 people. We already have about 25 questions that they've submitted, and we've got very little more than 5 minutes to go. So we won't get to all the questions today, but we'll send all of them to Joe in a spreadsheet. He will answer them, and we will post them on the website and perhaps even in our print magazine. And so continue to ask questions if you have additional ones. Just to fill out the 6 minutes that we have left, Joe, it's hard to decide which questions to choose, but just to start, someone asked, what percentage of a plant's power bill does the air compressors typically constitute?
That's a very good question. So I actually had a slide. So from my experience, which is again mostly the automotive, it can be anywhere from 10% in the component plants that you have up to 30%, even 40% in the stamping plants, depending on how large and what kind of presses they have. And then there's some companies that it's a huge part of it. If you take companies like Air Products that produce different types of gases that they have, that make the CO2 and the industrial gases, theirs is actually 90 to 95% compressed air because they use air compressors to do their systems. So they have a huge amount that's in there. So it really does vary from industry to industry. So you really need to understand not only your industry, but if you're working in a lot of different ones. I had the opportunity in my last role at Ford to have a group of that went out in the supply base in North America, and my teams would go out and help implement with Lean. And so I had the opportunity to get to learn a lot of the different processes that are out there. So it really does vary widely on the type of automation that they're using, what they're actually using air for, and what the requirements that they have are. So, but it can be anywhere from 10% up to 5 or 10% up to 40, 50%, and even as high as 80, 90%, depending on what their processes are. So unfortunately, there's not a fits-all for that question.
Well, thanks, Joe. Another question. What's the general rule of thumb for receiver storage capacity as opposed to baseline system usage?
That's a good question. In the compressed air challenge, we're recommending 5 to 10 gallons per CFM. And that's a lot of that's with load unload compressors to be able to make sure that they have enough time. The receivers originally for the old recips were sized at about 1 gallon per CFM. So we see a lot of undersized storage. And then, it got up to like 3 gallons per CFM. But ideally, that's, that you want to be in that 5 to 10. Really, it comes down to economics too. Can you afford to put that much in? I know there's a lot of people that will argue there's no such thing as too much storage, and they're probably right. I haven't seen it, but from can I afford to put it in? That's where it gets to be a little trickier. And that, again, that's one of the things we do cover in CAC training is what does that look like and how do you calculate those costs?
Good, thank you. What is the best way to gauge the size of leaks if I do not have an ultrasonic meter?
Another great question. What I would do is I would first start with doing what we call a leak load as part of the baseline. So what does that mean? That basically means that when you go into your operations, if you have the ability to go in on a holiday where no production is being run, how much compressed air are you using then? Go through and look at what's being done. If you have a meter, put a meter on it. See what your flow is. If you don't have a meter, you have load unload machines. Time the cycles to say whether or not how much am I loaded, how much am I unloaded, because that'll give you the amount of loaded time versus unloaded time will give you the percentage that you have on there. So it depends on the type of air compressor, this is what you do with the leak load and how you do it. On modulating machines, you have to estimate the volume of the system and then do a pressure decay on the system. So again, these are some of the things that we do in the compressed air challenge training. But my point is, it's really key to understand how much you're using on those times where you're using absolutely nothing, and to really be able to then put it into dollars when you go through and do that.
Well, thanks, Joe. We're going to have to make that the last question for today. As I mentioned, though, you'll have a chance to have your questions answered. Just check on the website in the near future. Joe, I want to thank you for really giving an outstanding presentation. Thanks so much for sharing your time and expertise. I'd also like to extend special thanks to our sponsor, UE Systems, for sponsoring today's event. And now that we're just about done, we'd like to hear how we did. The exit survey will pop up on your screen as soon as the webcast ends. Please take a moment to complete it because we use this information to improve our webinars. Finally, on behalf of Plant Engineering and UE Systems Incorporated, I'd like to thank you for attending. This concludes our webcast, and we'll see you next time. Bye-bye.